So it's a time. Time is 3 p.m. So we can start with the today's dot solving session. Currently, we are in the week 5 of Introduction to Material Science and Engineering course, and where we have studied the list of the content, which are as follow. This particular week was mostly related with the defects. Defects when like it can be the nature of defects can be point or 3 dimension or 2 dimension or 1D defect also. So it is mostly the imperfection in the crystals that we have understand overall. So we went through the vacancy, we went through the dislocations, particularly we went through edge, screw, and mix dislocation. We classified them based upon the relation between the Burgess vector and the tangent vector. Based upon the, the angle between them, if they are 90 degree, they are perpendicular, then we will call them it's the edge. If they are parallel with each other, then we will call it a screw. If they are neither perpendicular nor parallel, in that case we call it a mixed dislocation. In general, in our crystal, it is always the mixed dislocation which is present, the combination of the edge and the screw. Then we discuss the Burgess circuit, and later on we discuss about the energy associated with the dislocation line. We formulated that energy is associated with the dislocation line can be given as half b square. Okay, this is a shear modulus, this is a Burgess vector. We can say this is the magnitude of the Burgess vector and we are making the square of it. This is energy per unit length. Okay, and later on we talk about the Burgess vector, like at a particular node, how the Burgess vector is going to behave, how the Frank rule we have learned that at the particular node, we will add all the Burgess vector, the summation should come to be 0. Okay. So these are the list of the content that we have covered in this particular class in this week 5. If you have any doubt in the concept, please let me know so that we can discuss it. If not, let's move ahead to the next part where we are going to solve a couple of questions. Yeah, please go ahead.
Sir, that Burgess circuit, can you explain that once more?
Burgess circuit. Okay, this part. Sure. What we'll do is, let's make a crystal. So now we can see that I made a lattice, and where this particular is a dislocation line. Here is a defect. In this particular region, we have a defect. If I try to see below, we can see that the lattice is continuous. We are not able to see any defects over here. Also above, we are not able to see any defects. Right? Only the defect is present somewhere in between. So what we'll do, we'll try to count from here. Let's start from here. 1, 2, 3, 4, 5, 6. By the amount of 6, we went onto the right side. Then 7, 8, 9, 10, 11, 12, 13. Now let's go back. We went 13, now 14. Sorry, now what we have to do, on this we went by the 6. Here also let me write the same number. From here we went 1, 2, 3, 4, 5, 6, 7. So by the amount of 7 we went down. Now let's go back. we need to go back by the amount of what 6 1 2 3 4 5 6 7. 6 plus 7 is overall 30. So now let's start. 1 2 3 4 5 6 7 8 9 10 11 12, and then we can see 13 is somewhere ending over here. Okay, so here we went by the amount of 5 only. Here we went by the amount of 6. So what we are able to see, we are not ending. I think I should explain in again. Or better we take the example of the what professor has taught us. Budget circuit. Yeah. So what he has done, what we here it has been done is
around a distance.
we made a lattice, and we know that here we have a defect in this particular region. From this particular point, we started 1, 2, 3, 4, 5, 6. Like we are counting the steps 1, 2, 3, 4, 5, 6, so on and so forth. We counted 16. The number of steps we have counted here. Okay, I was counting the number of the atom. So we'll counted the number of steps. So now here we again started 1, 2, 3. We went by the amount of 10 to the downside. We went by the amount of 16 to the left. Now again we start here. 1, 2, 3, 4, 5, 6, so on and so forth. We went to the 16. Then again we went by the amount of what we say 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When we went here, what we realized that our starting point and our ending point, it is not coinciding. While in the perfect crystal, if I take the cube of 4 by 4, if I take a perfect cube, let's say 1, 2, 3, 4, 5. I'm just taking less number of points because we don't have that much of time. So let's start step 1, 2, 3, 4. 4 we went by this particular amount. Then here 5, 6, 7, 8. We went by the amount of 4 here and then by 8 over here. Now let's try to go back. 1, 2, 3, 4, 5, 6, 7, 8. So the point from where we started, the starting point and our ending point is coinciding here. So this is what tells that okay, the crystal is perfect. So here we can see that what I have drawn, I not draw any defects over here. I only draw 5 atoms here, then 5 here, 5, 5, and again 5. So this is a perfect lattice. But what we can see in the class that the video professor which has made, we are able to see when we went by the amount of 16 here, we came back by the 16, and we went by the amount of 10. When we came back by the amount of 10, we realize that our starting and the ending points is not same. It means that there's some defect it is having. So constructing this, now what we will do, we'll go start from the start point and we'll make a vector to the, from the finish point we make a vector to the start point, and we will call that to be the Burgess vector. So like let's say this is my finish point and this is my start point. So what I will do, if I want to find the Burgess vector, I will see by what is the distance between them. The distance between them will be the magnitude of the Burgess vector, and the direction will give the Burgess vector along which it is oriented. Okay. So this is the entire thing about the Burgess vector. So if any particular crystal is given to you having defect, what you have to do, you have to start counting from a particular step, go toward the right side, by the certain amount go toward the down, and then again you try to go back by the same amount. You have to make sure that the counting remains same. Let's say you went from the left to the right and top to the bottom by the
Sir, the Burgess circuit is not completing.
Sorry.
That means if the Burgess in Burgess circuit is it's completing the loop or not completing.
Yeah. So if it is completing or it is not completing, that is the something which will define whether the defect is present or not. If the Burgess circuit is completed, it means that there is no defect. So the Burgess vector, the magnitude will be 0. If it is not, if the circuit is not completed, it means that it is having some defect, and so we will call that okay. And the amount by which the circuit is not completed is the magnitude of the Burgess vector, and the direction in which we have to move will define that the direction of the Burgess vector. So this is the while by making the Burgess circuit, we can define what is a Burgess vector and what is its direction. Okay. So this is the entire thing about the Burgess circuit that we need to learn about. Okay. So if it is closed, then it's a perfect crystal. But if it's failed to close, then it means that some defect is there in it. Is it clear?
Yes, sir. Yes. Sir, one more thing that was in class, the sir has discussed about the tangent vector. Can you explain that vector, tangent vector?
Yeah, great. So let's say I'm having a dislocation line. Dislocation line is like this. It can be edge, it can be screw, it can be mix also. What is the tangent vector? Tangent vector is always along the dislocation line. So here, let's say that this is my entire dislocation line. So here the tangent vector is like this, along the dislocation line. All we have to do is make a tangent along that particular thing. Here the tangent will move along this. So tangent vector, what we have learned, the property of the tangent vector is that it will always be along the dislocation line. And if the dislocation line is changing, the orientation is changing, so do the tangent vector will also change. It is like what we can say, the tangent vector is tangent to the dislocation line. Tangent vector is tangent to the dislocation line. The dislocation line can be edge, screw, or mix, it doesn't matter to us. This property will always be satisfied. Now let's say my dislocation is like a circle. It's a closed loop. We know a tangent on the circle will be like this. At any particular direction, the tangent will be, we can construct a tangent to the circle. So this is the tangent vector. It will keep on changing its orientation.
Direction, right?
Yeah. Great. Is it clear?
Yes, sir.
Yeah.
And sir, one more thing that is in screw dislocation, sir has told about the spherical ramp, how it's going to have. But in edge dislocation, if there is any specific thing about how the edge name is comes.
Sorry. Can you please again explain?
Sir, on the screw dislocation, sir has told that while going through that, it forms a screw like spiral like shape. So that's why the name has given the screw dislocation. Is there is any specific like how the edge dislocation edge comes from?
At this location, we can see what we can see like it's an extra edge over here. So the atom was here, present. Suddenly we saw there is no atom is there. So what we are seeing it's like an edge. Nothing is there just below it, right? We call like this is also an edge, right? After this particular point, there is no atom along this particular plane, this particular paper. So it is an edge about, and just below that particular thing, we will call it to be the edge dislocation. Screw is making the screw, and edge dislocation is just below the atom. We are seeing that below the atom there is nothing. So it's like an edge. Edge has been created at this particular point. So we are calling as the edge dislocation. So name
Okay, sir.
tells lot of things. Yeah, that's right. Yeah. Any other question, Omkar?
No, sir.
Great. So now what we can do, we can move ahead and we can try to solve a couple of questions. Initially, it will be very easy. Then later on, we can increase the level of questions little bit. So now, let's try to see. Question number 1. Which of the following is an example of zero-dimensional defect? Dislocation, vacancy, grain boundary, or it's a stacking fault. So these are the
Vacancy, right?
yeah, it's a vacancy. So vacancy, we can say it's a point defect. So in the vacancy, we know that it can be. We saw the couple of defects in the vacancy. We saw the Frankel. We also saw the Schottky. Frankel is the one where we saw that an cation will move from its site and it will go to the interstitial position. In the Schottky, we know that the pair of the cation or a pair of the cation and the anion, cation, for example, NaCl, if I am talking about, here the cation is Na plus and the anion is Cl minus. So this pair will be missing. So it will be missing.
Sir, in this, which one is electrically neutral one? Frankel or Schottky?
Electrically neutral.
Is one question.
Electrically neutral, see.
While the anion and cation are missing, which one? In our class, one sir told like which one is the electrically neutral one, like that.
Electrically neutral, see, our material should be electrically neutral, that is 100% sure. Now, for example, the crystal is made up of the NaCl. So Na is positive and Cl is negative. Now what I am doing, I am removing both of them from the lattice position, and they can go to the surface also, that doesn't matter. They can go to the surface or they can leave the lattice itself. They can leave the entire system. So what we have removed, we remove the sodium, Na plus and Cl minus both. So the specimen is what? Again neutral. Now let's talk about the Frankel. What I'm doing in the Frankel, I'm taking the cation, let's say cation I took sodium. What I'm doing is that I'm taking it to the vacancy side. Na, it is going to the, interstitial it is going. And interstitial initially had no charge, but finally it will have some charge. And then it will also going to the, what we can say, it is, the vacancy has been created at the sodium side. Okay. In both the cases now, initially the vacancy had zero charge, no charge. Finally it will have the plus 1. Initially it has 0. So we can see here, initially vacancy is created. Why it is created? Because sodium has moved. So sodium has initially plus charge. Finally it has 0 charge. So if I subtract final minus initial, I will get minus 1. Here I'll get plus 1. Right. So overall charge, if we talk about, sodium is going to interstitial has 0 charge. And it is going plus 1 charge. So it is positive charge. So it should remove the vacancy. Yes. So both of them will have the charge neutrality. No matter what defect we create, we always make sure that our system, our crystal, should remain charge neutral. It never happened that I created some defect and due to which I am creating additional charge onto the system. So my system will always be charge neutral. Okay. So
okay, sir.
There is we can write lot of defect reaction at all, but defect reactions, but that is not covered in the class. So I'm not able to use the entire nomenclature. But once we cover that part also, then we can use the defects reactions. So overall conclusion which we will remember is that whether it's a Frankel or whether it's a Schottky, whatever the defect that we are creating, our crystal should remain the charge neutral. we are not adding any other additional charges, effectively overall.
Okay, sir.
So the question here is that zero dimensional defect. So zero dimensional defect is a vacancy. Grain boundary, it's a two-dimensional defect. Stacking fault is again the two-dimensional defect. A dislocation is a 1D defect. Right? Okay. Great. Now
Yes, sir.
let's move ahead to the next part, question number 2. Which of the following defect always exist in a real crystal due to the finite size? Now the important thing is finite size is given. Which of the following defect will always exist in a real crystal due to the finite size? We know all the crystals that we take. Let's say you are talking about.
In all real crystals, defects are there, right, sir?
Yeah, but which of the defect will be there? And which is coming due to the finite size? That is the question here.
I don't know, sir.
Yeah, great. No problem in that. See, whenever we are talking, let's say we are taking a crystal, any crystal. So what it has? It always have a surface. Surface means finite size. Finite size means a surface is there. Surface is nothing but a defect. Because at the surface, we know the bonds are broken. We know if I take the inside atom, it will be bonded with the n number of bonds. While if I am taking the atom at the surface, what we can see, it is only bonded with the one. It is more or less bonded with the less number of bond compared to the which is at the inside. So the broken bond which is here, this bond which has been broken, this is nothing but a defect which is coming due to the finite size. So here the answer will be the free surface.
Sir, can you explain that once more?
Yeah, great. So what I'll do, let us say that we have any metal. This is a scissor, and this part is a metal. Okay. If I see along the thickness direction, along this particular direction, what I'll see, I'll get, it is looking something like this. This is a surface. And this is the bulk, interior part I'm talking about. In the bulk, let's say it is making the 4 number of bonds. One is top, bottom, left, and right. Now, if I talk about the atom which is at the surface, let's say we are talking about this particular atom, it is making one bond here. Let's say it is making one bond here and here. This bond is broken. It is not attached with any particular atom. So this is what, it is nothing but a broken bond. And broken bond is a defect. A surface will always happen. The surface will always be there because of the finite size of the sample. If the sample is infinite, let us say you are talking about a world where a crystal is there which is infinite size. In that way, it will never have a surface. And so it will be perfect. But in the reality, in the real crystal will have a finite size, and finite size is something which will lead to the surface. And the surface atoms are broken, which is a defect. Clear?
Yes, sir.
Great. Let's move to the next part, question number 3. We'll solve it one by one. True and false. A perfect crystal exists in reality without any defect.
False.
False. Just now we saw that a defect will always be there. Let's move ahead. A free surface is considered a defect because it abrupts the periodicity.
True, right?
Yes, true. Because it is disturbing the periodicity. Inside atom, above there is an atom. Then again, in all the direction there is an atom. But here, if I talk about the surface, just above the surface there is no atom. So the periodicity is disturbed. Let's move ahead. Vacancy and the interstitial defects are classified as the two-dimensional defect.
False.
False. So which dimension it is?
One time zero dimensional, right?
Zero dimension. Yeah, good. Let's go ahead. Dislocation is a line defect.
Yes, right.
Yeah, true. It's a line defect and it's a one-dimensional defect.
Okay, sir.
So with that, we have solved this question number 3. Let's move ahead.
Sir, one more thing, that in substitutional impurities defect, that is the atom is replacing the, if there is a crystal of one atom, specific atom, is the one atom, another atom is coming or above that, it is placing in above or replacing that atom.
If we are talking about substitutional, we have solvent atom, and we have solute atom. Solute, which is like a impurity, and this is the pure. Let's say we are talking about the NaCl is the sample. So now what will happen? Let's say I am adding the potassium in that. So what will happen? Sodium was there, chlorine is there, chlorine, Na, Cl. So now if I'm talking about the substitutional, what will happen? This sodium will be replaced with the potassium. So sodium will leave and the potassium will come. This is a substitutional.
Okay, sir.
If we are talking about the interstitial, not substitutional, what will happen? This
It goes to the industrial space, right?
Yeah, it will come somewhere over here. So it is replacing in the substitutional, and it is just going into the interstitial side when we are talking about the interstitial defect. Great. Okay, let's move ahead to the next part. Why must there be a certain fraction of vacancy in a crystal at equilibrium? Certain fraction of the vacancy will be there in equilibrium. Why?
Because to minimize the Gibbs free energy.
That's right. Because it's minimized the Gibbs free energy, it adds the configurational entropy. So the perfect crystal, if we talk about, where there is no point defect, let's say no point defect. And the second case is the one which is the real crystal, which has the point defect. Real crystal is more stable than the perfect crystal. And the reason we know that Gibbs free energy of the real crystal is lower than the Gibbs free energy of the perfect crystal. Okay, so it minimizes the Gibbs free energy. Very good. Let's move ahead. Let's try to solve more questions. If you have any doubt, please let me know. Which of the following is true about the Frankel defects? Now we are talking about the Frankel defect. It involves a pair of a cation and an anion vacancy. It involves a cation moving to an interstitial site. They are only found in the metals, none of them.
The both them are in industrial side, right?
Cation will move to the interstitial side. Yeah.
Anion is also moving, right?
No, anion
Both
is anyone. So cation is the one which will move to the. If cation is moving to the interstitial side, we'll call it to be the Frankel defect. It's a Frankel. If anion is the moving to the interstitial side, we'll call it the anti-Frankel. I think this term is not introduced in the class.
Yes, sir. Only thing said that the both of them are moving to industrial side, it is called a Frankel defect, right?
No. If both of them are moving towards, both of them are leaving the lattice, then we'll call it to be the Schottky defect. In a Frankel, cation is the one which is moving to the interstitial. Okay, Na plus, it moved to the interstitial side. Okay. If both of them are moving, then we will call it to be the Schottky defect. Okay.
Both of them are leaving from this crystal lattice. It is called Schottky, right?
Yeah, it can go to the it can either go to the interstitial, it can go to the grain boundary, or it can go to the surface, or it can leave the lattice. If both of them are moving, we'll call it to be the Schottky. If one of them, like cation is the one moving, then we'll call it to be the interstitial. Sorry, cation going to the interstitial side, we'll call it to the Frankel. Anion moving to the interstitial side, we will call it the anti-Frankel. Cation and anion, both of them leaving the lattice, or it's going to the surface, then we will call them as a Schottky. Okay.
Sir, one more thing that is in Schottky defect, it is leaving, right? Not on the industrial position, right? Industrial space.
It is, yeah, we can consider that to be, see, it can even go to the grain boundaries also. So grain boundary can also be act like a, we can consider them as an additional surface. And we can surface also, we can consider them the additional surface. So if it is moving, both of them are leaving the lattice together and going to certain defect. It can be the surface, it can be the grain boundary, then we'll call it to be the Schottky.
Okay, sir.
If it is moving to the interstitial side, cation moving to the interstitial side, we'll call it to be the Frankel. Anion moving to the interstitial side, we'll call it to be the anti-Frankel. Okay.
Okay, sir.
Great. So with that, I think the right answer is option B. Let's move ahead. Let's go to the next question. Question number 6. Yeah. It's a mass pair type. Vacancy, Frankel defect, Schottky defect, Gibbs free energy.
One matches the C, right?
Yeah. Vacancy, a vacant site in the crystal. 1C. Frankel defect.
Option D.
Option D. Great. Schottky defect.
B.
Option is B. And the Gibbs free energy we know.
Fourth is A.
Yeah. Great. So the answer will be C, D, B, and A. Great. Let's move ahead. True and false. A perfect crystal with no vacancy can exist at absolute zero. Any?
I think it's false, right? Or I don't know, sir.
Yeah, no problem. See, we know that small n divided by capital N will be equal to the exponential minus of delta H F divided by KT. This is the equation. N is the vacancy concentration. Capital N is the number of atom. Now let's see this particular equation. Small n divided by capital N will be equal to the exponential of minus delta HF divided by KT. Now consider like absolute zero we are moving, T is tending towards the 0 Kelvin. So what will happen? This entire thing will tend towards the infinity. With the minus sign, they will tend towards the minus of infinity, exponential of minus infinity. So the value of the exponential of minus infinity, we can write the 1 divided by exponential of infinity. Exponential to the power infinity will be nothing but an infinite number. 1 divided by infinite number will come to be 0. They will tend towards the 0. So small n divided by capital N will tend towards the 0. We can say that n is tending towards the 0 when T will tend towards the 0. So at the absolute temperature, when the temperature is tending towards the absolute 0, the concentration of the vacancy will also be tending towards the 0. A perfect,
so it's a true one.
Yeah, so it's a true. Very good. A perfect crystal with no vacancy can exist at absolute 0. Let's go to the next part. B. The equilibrium concentration of the vacancy decreases with increasing the temperature.
False, right? Increases with the increase in temperature.
Absolutely. Great. So since we were decreasing the temperature we were decreasing and was decreasing, right? T was tending to 0 and is also tending towards the 0. If I increase the temperature, my N will also increase. So this is false.
Sir, in all the defects, increasing the temperature will result in increasing the vacancy, right?
Yeah, in all of them. If
Okay,
you
sir.
increase the temperature, it will happen. Yeah. Whether it's a metal or if you can consider the ceramic or anything, the temperature increase will lead to the increase in the concentration of the defects. Again, we are talking about the point defect. Third part. The Frankel defect involves the movement of the cation to an interstitial site.
True.
True. C part. The Gibbs free energy of the crystal with the vacancy at equilibrium is lower than that of the perfect crystal.
False.
It's true, right? Gibbs free energy of the crystal with the vacancy at equilibrium is lower than that of the perfect crystal. Right. I think we have discussed over here. Gibbs free energy of the perfect crystal is higher, and the Gibbs free energy of the real crystal, which is having the defect vacancy, it is lower.
Yes, yes. I remember now.
So this is true. Last part. Schottky defect involve the creation of the single cation vacancy.
False.
False. It will lead to the creation of both the cation and the anion vacancy. Okay. True, false, true, true, and false. Great. Let's move to the next part, question number 8. What is the primary characteristic of a dislocation line? It is a planar defect, point defect. It is a line with a small diameter and the long length. It is a surface defect.
It's a line with a small diameter and long length.
Perfect. Okay, it's a 1D defect. Let's move ahead. What is a slip plane in the context of the dislocation? A plane where no slip occur, a plane where the crystal is cut and slip occur, a plane where dislocation are eliminated, a plane where the crystal lose its symmetry.
Option B, right?
Option B.
The plane where.
Yeah, very good. It's option B. So we have saw that in class, this is a dislocation line and this part is the slip part and this is no slip. What happened? We cut this particular plane and this slip plane and then moved it. So we cut the crystal and the slip occur. So this is the option B is the right answer. Let's move ahead. What is the significance of the tangent vector? This is something which we have discussed initially at the beginning. It describes the magnitude of the slip. It describes the orientation of the dislocation line.
It describes the orientation of the dislocation line, right?
Yeah, option B is the right answer here. It describes the orientation of the dislocation line. Great. Let's move ahead.
Sir, one more thing that in edge and screw dislocations, we are cutting the plane, right? We are making that defect, right?
Yeah.
Not on making of. Not itself is making, right? We are making that defect, right?
On the paper we made, but in the real crystal will make. So what we are trying to do with this particular model that we have studied, okay, we cut the plane, we moved it. This is a way for us to understand. So crystal will happen. The defects will always be there. If the dislocation has been there in the crystal, it means that this slip has already occurred. It's not the we are doing. It's the external condition. Let's say what will happen if I take a metal, this metal, and I'm taking the hammer and I'm beating it multiple times. What I'm doing, I'm creating the hardening, I'm creating the additional stress in this specimen, I'm creating the dislocation. So it's the external stimuli which is doing this thing. If I take a hammer, if I beat it, if it is a copper wire, you can see, take a copper wire, try to bend it. Now if you try to again bend it, now you will require more force. So there was a couple of video from the MIT on the YouTube which a girl was trying to do is she took the copper wire, she tried to bend it. Initially it happened. Now the dislocation came and it made it so harder that again she is not able to do it. So initially what happened? They created the dislocation. So it can be external stimuli. The stimuli can be electric field, stimuli can be the temperature, stimuli can be the additional applied force. Okay. This external stimuli can lead to the creation of the dislocation which is occurring by the slip. Okay.
Okay, sir.
Yeah, great. Now, if the slip occur in the lattice translation way from one lattice to another, then it's a perfect dislocation. If not, then it is a partial dislocation, which we have studied in the class. Perfect dislocation is what we have studied, the edge dislocation. Partial dislocation will lead to the creation of the stacking point, which is again we are going to study in detail later on. Yeah, so this question was on the orientation of the dislocation. Let me know if any doubt you have.
No, sir.
Great. Let's move ahead to the next part, question number 11. We just discussed about the tangent vector. Now let's discuss about the Burgess vector. What does the Burgess vector represent in the dislocation?
The magnitude and direction of slip.
Yeah, it's the magnitude and the direction of the slip. Orientation of the dislocation line is the tangent vector. Energy of the dislocation, no. Plane of the dislocation, no. Great, let's move ahead to the next part. Question number 12. The relation between the different dislocation and their Burgess vector and the tangent vector, we have to discuss that. Edge dislocation, first one.
Perpendicular to the tangent, right?
Perpendicular to the tangent. So B will be perpendicular to the tangent. That is option A. The screw dislocation.
Parallel to tangent.
Yeah, and the last one is this itself.
Mix.
Right. So mix will always be. It will neither be
Either perpendicular or parallel.
Yeah, great. In the assignment, the week 5 assignment, the last question you can see, it is something like this. A and B points are given and they are trying to tell us that what will be about the relation between the B and T at the particular point P. All you have to remember while solving that question is that the tangent vector is along the dislocation line and it can move depending upon the dislocation. Here the tangent can be like this, here it will be like this, here it can be like this. But the Burgess vector will remain constant. Okay, so with that, the relation between the B and T, Burgess vector and the tangent vector, you can find whether it's an edge, screw or mix. Let's go ahead to the next part, question number 13.
So Burgess vector is always constant.
Burgess vector will remain constant, yeah.
And tangent vector will be always changing with the respect to dislocation line, right?
Yeah.
Okay, sir.
Yeah, great. Now, in the context of the Burgess circuit, what is the relation between the closure failure and the Burgess vector? The closure failure is perpendicular to the Burgess vector. The closure failure is equal to the Burgess vector. The closure failure is unrelated to the Burgess vector. The closure failure is a tangent vector.
The closure failure is equal to the Burgess vector, right?
Burgess vector, yeah. Great. The closure failure is nothing but a Burgess vector itself. Okay. So it also tells about the magnitude and the direction of this particular Burgess vector, not the tangent vector. Okay. This is incorrect. So with that, we'll solve this 13th. Most of the answer I'm keeping B only. I think I should change later on. Fine. What is the primary cause of the elastic strain energy around the dislocation? We saw that elastic strain energy was there, which was half shear modulus and the Burgess vector square. The presence of the impurity, the strain field created by the dislocation, the temperature of the crystal, the grain boundary in the crystal. Elastic strain energy around the dislocation line. Here, what we can say that it is a strain field which is created by the dislocation itself. We saw a dislocation. Above we know that it's a compressive stress. Below we know that it's a tensile stress. So around this, there is a stress field. The strain field is there, which is nothing but it is created by the dislocation itself. So the primary cause of the elastic strain energy around the dislocation is the strain field, which is created by the dislocation. The strain is there. The above part is compressed, and the downward part, the below part of the dislocation is the little bit elongated. Right.
Okay.
So with that, it is creating a strain, which is relating to the elastic strain energy. So this we will remember. This lot of questions can be asked from this in the final exam, or I saw in couple of the gate exam also they ask this type of questions.
Okay, sir.
All we'll need to remember is the Burgess vector for the FCC, BCC, and the simple cube. Okay, let's move ahead. What is the unit of the line energy of a dislocation? What do you think? What will be the right answer here? Energy
Energy per unit length.
per unit length. This is the important. People think that it's a volume, but no, it's a length. So energy per unit length. It's option C. Okay, great. So with that, this we can match. Let's move ahead to the next part. Question number 16. What happens if the Burgess vector is not a lattice translation? This is something which we discussed. Burgess vector is nothing. It's telling that the magnitude and the amount by which the slip has occurred. If slip occur from one lattice point to the another lattice point by this much magnitude, then it's a perfect dislocation. And if, let's say this is a lattice point, but slip occur only by this much magnitude. Initially it was like this, this atom came over here. The slip has not occurred by the amount of the lattice translation, then what we will say, it is a partial dislocation. This partial dislocation lead to the creation of the stacking plane. So what we can say, what will be the right answer here?
Option B will be the right.
Okay, great. Let's move ahead. Next part, question number 17. So we were discussing that in this particular equation of half v square, we need to know Burgess vector. So for the simple cubic, what will be the Burgess vector? So we have to draw simple cubic, let's say. It's a pure geometry. What we have to know is that what is the smallest distance between the two lattice point? Let's say that the lattice parameter is A. What is the smallest distance between the lattice point, two lattice point? Let's say this is a lattice point 1, and which is the most nearest lattice point? You can say it's this one.
Sir, all are in equal distance, right?
All are in equal distance. That's right. But no, what about this point and this point?
Yes, it's difference.
Different, right? So the nearest lattice point to this is this one, this one, and this one. Okay. Let me mark with the red. And again, behind will be there, this side will be there, and this side will be there. Now, what is the distance? What is this much distance? It is nothing but a lattice parameter A. So I can say that the Burgess vector, for the Burgess vector, what we need the magnitude as well as the direction. So magnitude is from the lattice translation A divided by A. What about the direction? Direction is along, we can say that 1, 0, 0 or 0, 1, 0, 0, 0, 1. We know that all three are same because it's a cube. They are the family of the direction. So what we will get from here is that it will be the 1, we'll get 1 0 0. Simple cubic will be matched with the C. What about the BCC?
It matches the B, right?
Yeah, BCC will match with the B. Great. Because we know in the BCC there is an atom at the center. So now the nearest lattice is nearest atom from this for this particular lattice point is this one, which is nothing but the half of the body diagonal.
Okay. Distance.
Yeah. So it will be the half of 1 1 1. Great. FCC
Matches A, right?
matches A. That's great. Now the NaCl. What is the to answer this? What is the Burgess vector of the NaCl? We need to know what is the crystal structure of the NaCl.
I don't know, sir.
Yeah, it's a rock salt structure. That's fine. We know that it is the lattice is made up of the FCC. Since the NaCl lattice is FCC, so the Burgess vector will also be will follow the FCC.
Option
A. Now the question can ask for the CSCl also. The crystal structure of the CSCl, we know it's a simple cubic, where we say that chlorine is at the corners and the CS will sit at the center, and it's a simple cubic structure. So it's the lattice parameter of the Burgess vector of the CSCl will be same as 1 0 0. Okay, great. So with
yes,
that,
sir.
with that we have solved this question number 17. Any doubt in this?
Sir, should we mug up these vectors?
No, we don't have to mug up. What we need to do is we need to remember structures at least. NaCl I know it's FCC, and CSCl I know it's a simple cubic. So there are a couple of the standard structures. These structures are frequently used. So just by reading the paper, books, and all, you will get it in the mind. What we have to understand that corresponding to this structure, how this Burgess vector came. Right. So for example, for FCC, why 101 came? 101 came, why it is? So this is something which we need to understand. For the BCC, why 111 came? And for the simple cubic, why 100 came? Which we have understood. Okay. For the FCC, again, see, FCC will have one atom at this particular point. So the nearest lattice point will be now this. So this is how we can classify them. Okay, great. Any other doubt, Omkar?
Sir, apart from the NaCl and SCCl, any other molecules can you say?
Yeah. For example, MgO, they can ask. MgO is again, I think it's FCC again. Yeah, it's FCC. Okay. NaCl, there is a KCl, KBr, Ki. All of them are FCC. They all have the rock salt structure, like the NaCl.
Okay, sir.
Okay. There are the list of the materials. Okay, there is a lot of, but we have to understand for the couple of only basics and which are frequently used structures. Okay, great. Let's move ahead. True and false. The first part. The Burgess vector.
First one is true, right?
Yeah, first one is true. Burgess vector is always the shortest lattice translation. Great. Second part. A perfect dislocation is associated with the stacking fold.
False, right?
False. Great. It's a partial dislocation which is associated with the stacking fold. Next part. Energy per unit length of the dislocation is proportional to the square of the magnitude of the Burgess vector.
True, right?
It's true, yeah. We knew the formula. It's half g b square. It is the energy per unit length. Now, D. In a body-centered cubic crystal, the Burgess vector is 100.
False, right?
False. So what it is?
It is half of 111.
Yeah, it is half of 111. And for the FCC,
For FCC, it's half of 110, right?
110. Yeah. Okay. Perfect. See, now we learned it. Now last part. A pulsar dislocation is not associated with the stacking fault.
False, right? It will result in stacking fault, right?
Yeah, it is. Uh, they are more or less are the close question. I shouldn't have. Maybe I designed it wrongly, but okay, fine. It's a false. So with that, we have solved this question number 18. Let's move to the next part, question number 19. Which of the following statements is slash r true about the Burgess vector of a dislocation line? Burgess vector change direction along a curved dislocation line.
No, right?
No, it's incorrect. Burgess vector represent the magnitude and the direction of the slip.
That's correct.
That's correct. Okay, now next part, the Burgess vector is always perpendicular to the tangent vector.
That's false, right?
It's a false. Yeah, it will depend upon the nature of the dislocation. Okay, so with that, option B is the right answer here. Let's move ahead to the next part, question number 20. Which of the following statement are true about the Frank rule? The sum of the Burgess vector at the node must be 0. What do you think?
I don't know, sir. That Frank rule.
Yeah, Frank rule says that at any node we are talking about, let's say this is a dislocation line, this is another dislocation line which are meeting at the node, and here is another dislocation line. So let's say this dislocation line has the Burgess vector b1, this can have the b2, and this can have the b3. Okay, so what Frank rules say that summation of all the Burgess vector should be 0. It means that if you are talking about that the node n, so the b1 plus b2 plus b3 at the node, it should be equal to 0. There is another condition of the Frank rule. It says that all the tangent vector we know that it's a t, they all should either point towards the node, or they should all point toward away from the node. Okay, either they all should point towards the node, or they all should point away from the node. If it is not satisfied, we have to change few things. For example, let's say here is a case. This is a tangent vector t1. This is its Burgess vector b1. This is tangent vector t2. This is Burgess vector, let's say b2, and tangent vector t3. This is a Burgess vector b3. Okay. So at the node, the first condition is that all tangent vector, either they should be towards this particular node, or they should be away from the Burgess node. So see, this one is going away from, this one is coming towards, this one is coming towards. So what we have to do? Two are coming towards, let's make this also, let's change this direction. So now what will happen? What changes will make over here? T1 we not had any problem. Sorry, T3 we not had any problem. T3 will remain as it is. B3 will also be remain as it is. T2 will is pointing towards, so no problem at all. Here B2 is also no problem. So the problem was the T1. So we are changing its direction, T1. The thing is that if you change the direction of the T1, the direction of B1 will also be flipped. If you are flipping T1, remember this, if we are flipping T1, the B1 will also be flipped. And now we can apply. See, all of them are pointing towards the node. This is also pointing towards the node, towards the node, towards the node. Now we can apply B1 plus B2 plus B3. Their summation should be 0. So this is a Frank rule. First condition, all of them points, they should point towards the node or they should point away from the node. If they are not doing, we have to flip and we have to make them that all the tangent vector should follow that particular rule. If you are flipping the tangent vector, you will flip the Burgess vector also. This we will remember. So now we can answer this question. Okay, question was this. First, we know that the sum of the Burgess vector at the node must be 0. The tangent vector at the node must all point towards or away from the node.
That is true.
That is true, right? B is right answer. The Burgess vector of the dislocation remain unchanged even if the tangent vector is flipped.
No, right?
No, it's a false, right? It's correct. This is a false. Frank rule apply only to the straight dislocation line. This is false. It can be applied to all of the dislocation line.
Okay, sir.
So the option A and B was the correct. Great, let's move ahead to the next part, question number 21. What is the magnitude of the Burgess vector of a dislocation in the BCC crystal with a lattice parameter 4? So now we have to find the magnitude of the Burgess vector. Magnitude of the Burgess vector will be given as the A by 2 in the BCC 1, 1, 1. We have to find the magnitude of this thing. A by 2 we can take outside because it's just a scalar quantity. A is a 4 and 2 will be the 2. We have to find the magnitude of these things, which is nothing but root over 1 square plus 1 square plus 1 square. So it is 2 root 3. What will be the value of 2 root 3? Let's do it. It's a 3.46. The unit of A will be the unit of the B. It's an Armstrong. So we can say that right answer is option A. Is it clear?
Yes, sir.
Yeah, great. Let's move ahead to the next part. If they would have asked the same thing for the FCC instead of this thing, what I will write? It will be instead of 111, it will be 110, right?
Yes, sir.
Then it will be the root 2. Now let's move ahead to the next part, question number 22. Okay, here NaCl. What is the magnitude of the Burgess vector? Again, we have to find the Burgess vector magnitude of a dislocation in the NaCl. NaCl
is FCC, right?
Yeah, FCC. So what we will do here? A by 2. 1.
1, 0.
Yeah. So we have to find the magnitude of this. We'll take A outside, 2 outside. Here we have to find the root of 1 square plus 1 square. It is A divided by 2 root 2. It is A by root 2. 5.64 A value is given to us. 5.64 divided by root 2. Oh, 64. It's a 3.988. Approximately it is 4. Okay, so with that we have solved this for the NaCl also. Even so, one can just change this particular NaCl. KCl they will write, or MgO they can write. Okay, so these are the things they can make the changes. Let's move ahead. 23. The enthalpy of formation of the vacancy in the nickel is given to us. So delta HF is given to us. 75 kilojoule per mole. At what temperature would the vacancy concentration become half? And at the 100. 100 degrees Celsius, we have the vacancy concentration. We need to find the temperature at which the vacancy concentration will become half that of this particular thing. So n divided by n of 100 divided by 2. How can we do that? Delta HF is given to us. We have to find that the concentration at particular temperature, which is nothing but the concentration at 100 degrees Celsius, should be the half. Okay, so we know the formula. N divided by capital N will be equal to the exponential minus of delta HF divided by RT or
KT.
KT. But here they have used the kilojoule per mole. So what I will prefer is RT. Because
Okay, sir.
the mole. So we can substitute this thing over here. I don't know the temperature, but here we can write. Let's flip this 2 onto this side. 2 times of NT. It is given as the capital N times exponential of minus of delta HF divided by RT. Which should be equal to the N times of N of concentration, which is at the 100 degrees Celsius. So we'll write the concentration at the 100 degrees Celsius. And exponential minus of delta H divided by R. T we can write. We know the temperature, 273 plus 100. We will always use the Kelvin, absolute temperature values. N got cancelled out. So what we got here is 2 will be 2 times exponential of minus of delta H divided by RT is equal to the exponential of minus of delta H divided by 373 times R. Delta H we know, it is given to us. In this equation, only R is also given. R is a constant we know. Only the variable is T, which we can find. One equation, one variable we can find. So let's just rearrange the time. 2 will be equal to the exponential minus of delta H divided by 373R. This will go over this particular side, so it will be denominator, and then exponential will be added. This minus sign will come over, become plus delta H divided by R. So now we can take the ln on both the sides. So ln2 should be equal to the minus of delta H divided by 373R plus delta H divided by R times of T. We can substitute the value of delta H. Delta H is given to us 75 kilojoule per mole. Let me do it here. ln2 delta H I can take common, divided by, I will shift it this particular side. This is 75 minus of 1 over 373R plus 1 over R. R also we can shift. R is nothing but 3.14. It is kilojoule per mole. Let's convert this. ln2 75 000 3.14 will be equal to the 1 over 373 minus plus 1 over t. Now we just need to calculate this. Right. So with the help of the calculator, we can do this. I think we can stop it here. You can do ahead part. All we have to do is we have to just shift this particular thing over here, and we have to flip it so that we can get the temperature.
Okay, sir.
So this is the procedure which we have to follow. The procedure is important, and then the exact value what this question demand right now. Once we know how we do, then it's easy. So let me tell you, this type of question has been asked multiple times in the GATE and also in the previous year exam of this particular course. Okay, let's move
Okay, sir.
to the next part, question number 24. This is a Burgess vector. This is a PQ is a dislocation line. Burgess vector is given to us. We have to find whether it's a mixed edge screw or a prismatic loop.
It's parallel, right? So it's a screw.
It's a screw. Great. Okay. It was so easy. Let's move ahead. Next question, question number 25. Question number 25 we have the line energy is given, the line energy joule per mole of the dislocation in the CCP cubic close pack. It has the FCC structure, lattice. With A equal to 4 Armstrong and the shear modulus is given to us. We have to find the energy of G B square half multiplied by what is G? G is 200 given to us. Gigapascal we need to find in the joule per meter. We will convert it to the SI unit. We will multiply them by 10 to the power of 9. Multiplied by B square. B is the Burgess vector we have to find. So what will be the Burgess vector for the FCC?
Half of 110.
Yeah, so half of 110. We have to find the magnitude of this. A is given to us 4. 4 by 2 is nothing but 2 and it's nothing but the root 2. Right, root over 1 square plus 1 square. So here 2 root 2 we can say. We have to substitute this over here as a B square. We need to find the B square. It is 4. 4 times 2. It is 8. So what we can say that 8, but the unit will be nothing but Armstrong over here, right? So we have to convert the unit also. We'll convert it to the meter. So to convert Armstrong to the meter, we have to divide it by the 10 to the power of 10. Remember, it's a B square. So Armstrong will also come for the square. Now we can easily do it. This is 4. 4 2s are again 8. 8 multiplied by 10 to the power of 11 divided by 10 to the power of 20. So it will be the 8 multiplied by 10 to the power of minus 9 joule per
Option A is correct.
option A. Right? Great. So with that, we have solved this question. Let's move ahead to the last question of this.
Sir, how much question left?
Last question.
Okay, sir.
Great. Okay, for the straight dislocation line, if T is tangent vector is given, Burgess vector is given, which of the following can be concluded? The dislocation is a edge, screw, mix, or data is insufficient. So what procedure we have to find? We need to follow. Tangent we know.
Should we draw the sister structure, that vector?
That will not be that helpful. What we need to know, see, if we know that tangent vector, if it is perpendicular to the Burgess vector, it's a edge. If they are parallel, screw. If they are somewhere in between, then it's a mix.
Mixed one.
So what we need to find is the angle between tangent vector and the Burgess vector. Two vector is given to us. Tangent vector is 1 I cap. Burgess vector is 1 I cap plus 1.
Plus 1 is A cap.
Right? We can easily find the angle between them. Right? T dot B will be nothing but mod of T mod of B, angle between them cos of theta. So let's do the dot product of there. What we will get is a 1 I, j will be cancel out. So their dot product is 1 divided by magnitude of the T. Magnitude of T is 1 multiplied by magnitude of B. Magnitude of B is nothing but root over 1 square plus 1 square, it is 2. It is cos theta. So cos theta came to be the 1 by root 2. What will be the angle? Cos theta is 1 by root 2. So what is the theta? Theta will be equal to the 45 degree. Now it's neither the perpendicular, it's nor the parallel. So it is what is the angle between them is it's a mix. 45, it's a mix. So with that, we say that the option C is the right answer and the data was sufficient. It's not insufficient data. Clear?
Yes, sir.
So, Omkar, any doubt in the session that we did for today?
Sir, I have a doubt that in this section, is that sir will take about the APF factors, atomic packing factors.
Atomic packing fraction. I not got. Like, can you repeat again?
Sir, in first module, we have that part is in our syllabus. So, not on this MPTL exam, for our university exam, there is a part. So, I check on this YouTube that if you're having about that part, atomic packing factors, shall this section will discuss about that one in the coming section.
Okay, you're talking about the 74% atomic fraction, the
Yes,
vacuum.
yes, sir. That one.
Actually, that is something which has already been covered in the last week, I think. Last week or last to last week. So in FCC we got that it's a 74%. Then in BCC also we 68 we got, and then simple cubic is 50.
You said that that how we are finding that one procedure, right? There is a that part didn't take in the class, right?
That procedure will it's a pure algebra what we have to do. So so now for example that will not be covered, but what will say that I'll tell you that it's it's a
Sir, first year I got it, but the last one that is for hexagon and closed pack structure. That one,
yeah, SCP. It will be little it's little difficult, right? So what in SCP what we have saw that we made a tetrahedral, and on top of that particular tetrahedral is nothing but one atomicity. So what is the structure? See what we have drawn in the class, something like this, and then just above of this we again we draw. The angle is between them is nothing but 120 degree. We know this and we know this. Next thing what we saw in the class that this is nothing but a triangle. This triangle just above this particular triangle we have one atom. Sorry, above this particular triangle we have one atom which is forming the tetrahedron with this thing. Similarly, it is forming the tetrahedron with the top one also. So what we did, what we the algebra, I think algebra also we did over here. That sir told that certain part of that will be the homework. So if we consider this particular triangle, this base triangle, we know it's an equilateral triangle. The center of the equilateral triangle we can find considering this thing to be the edge A. If this is A, then this will also be A, and this will also be A. The center will be divided in the way that it will be the 2:1 ratio. Once we find this, see our aim is to find what? Our aim is to find the height of the tetrahedron. So once we find the height, we want to find the height of the tetrahedron and then how many atoms are there contributing in this particular tetrahedron. We know, Omkar, that the center is divided into 2:1 part. So an atom is sitting, this atom is sitting just above this. And the tetrahedron, the center of the tetrahedron, this will be divided in the height ratio of 3:1. If I draw a height from this particular thing to the base, this to the base, which is let's say here A, and here this point is a B. So B and A will be divided in the ratio of the 3:1. And with this particular geometry, we can find the what is the amount of what will the height of the entire tetrahedron. Once we find the height, then what we can do, just have to make the twice of that particular height, and you can find the volume of the unit cell.
Okay, sir.
So our entire the problem here is in a way that it's a pure geometry. It's nothing but a pure geometry. We know it's a 2:1, then it's a 3:1 geometry. We just have to uh, run paper, like pen on the paper, and we will get the answer. Once we find the height, once we get the volume of the unit cell, and we know how many atoms are contributing this particular unit cell, then we can find the packing fraction, right?
Okay, sir.
So this part will be like, it was treated as a homework. Anyway, do you have any other doubt, Omkar, other than the, like, anything else left? Any other doubt? Please feel free to ask me. No problem.
Okay, sir.
Yeah.
Sir, do you have a proper definition for defining grain?
Defining grain. Actually,
Yes, what is grain?
that
What?
yes, that part is coming. That the definition of the grain is been covered in the week 6. Currently, we are in the week 5. So, see, we till now what we have discussed, we discussed the zero-dimensional defect. We discussed the one-dimensional defect, which is the dislocation. Now we will move towards the, in the week 6, we will move toward the two-dimensional defect, which is grain boundary. Now to define the grain boundary, we will have a grain. Okay. So one grain is nothing but a one single crystal. One grain is a one orientation. Atoms are oriented in one particular way. Different grain, their orientation will change. Okay, so the grain boundary is a region between these two particular different orientations. So this thing we are going to discuss in the week 6. So I will suggest, like, we should join the next week week 6 dot solving session. We'll have a detailed discussion on this particular. This is very beautiful topic of the grain and the grain boundary.
Okay, sir.
Anything else? Yeah. Yeah. If any doubt, please let me know. Take your time.
Okay, sir. Sir, in vacancy defect, that atom is completely missing, right?
Sorry.
In vacancy defect, that atom will be in the place of that atom, it is completely missed, right?
Yeah.
Empty portion, right?
Yeah. It will be missing from its site, and it will go to some other site. Okay.
Okay, sir.
Yeah.
Sir, I think no doubts are there.
Okay. Great. So what we'll do is we'll complete this particular week 5 now. You try to attend the assignments question and try to submit them. If you face any problem in that, we can discuss in the next week, week 6. Also, along with this dot solving sessions, my aim is also to cover the assignment question which you have faced problem like week 4, week 3, week 2. So whatever the assignment question you are facing problem, we can also discuss that. So collect your questions. If you face any problem, any difficulty in solving them, we can discuss in the upcoming week. Okay. So with
Okay,
that,
sir.
we'll close this today's session and we'll meet again in the next upcoming dot solving session.
Sir, it's a nice section with you.
Yeah, it is. It is designed in a way that, for example, a professor, the video is only interacting in the one way, one direction. But the dot solving session is the essence of this is that the two-way discussion should be there, so that any doubt should be cleared. Yeah. So what we'll do is we'll meet again in the next week, week 6. The timing and the day will remain same, Saturday 3 to 5 p.m. And we'll try to discuss whatever the questions you are facing, Omkar. Okay,
Thank you, sir.
great. Okay, bye bye.